Okay, good morning, everyone. Today we'll begin section 11.2. We'll be looking at the theoretical probability of an event. So, probability is a measure of how likely an event is to occur. Each possible result of a probability experiment or situation is an outcome. The sample space is a set of all possible outcomes. An event is an outcome or set of outcomes. So, for example, if I have a number cube, I have 6 possible outcomes. I can roll 1, 2, 3, 4, 5, or 6. The sample space would be 1 through 6. If I'm spinning the spinner here, it has 4 different colors. The sample space would be red, blue, green, yellow. I would have 4 total outcomes. Probabilities are written as fractions or decimals from 0 to 1, or as percents from 0% to 100%. So probability can range anywhere from 0, meaning you have 0% chance of an event happening, to 1. You have 100% chance of it happening. Equally likely outcomes have the same chance of occurring. When you toss a fair coin, for example, you can get either heads or tails, and that's equally likely you will get either one of them. Favorable outcomes are outcomes in a specified event. For equally likely outcomes, a theoretical probability of an event is a ratio of the number of favorable outcomes to the total outcomes, total number. Okay, so for equally likely events, the probability of an event is the number of favorable outcomes divided by the total number of outcomes in a sample space. Okay, or the way I like to say it, I just say is the probability of an event is equal to the event space divided by the sample space. Now, the type of probability we're going to be working with is not the simple probability you're used to. Okay, because favorable outcomes are the event space. There's multiple ways in which you can find the event space. Enumerations, which just means you just have to count things. You can use the fundamental counting principle, which says if there's m ways to choose one thing and n ways to choose another, then there's m times n ways to choose them together. Or the favorable outcomes or event space may involve permutations or combinations. And then for the sample space, again, you define the sample space by either using the fundamental counting principle, permutations, or combinations. Okay, so the examples I will go through will be using one of these ways in which to find the event space and the sample space. Sometimes we'll have to enumerate. Sometimes we'll have to employ the fundamental counting principle, which I will denote as FCP, or permutations or combinations. So let's look at the first example. A CD has 5 upbeat dance songs and 7 slow ballads. What is the probability that a randomly selected song is an upbeat dance song? Okay, so the probability of an upbeat dance song, well, the total number of outcomes you have are 12. You have 12 possible songs. Okay, what's the event space? What is the favorable outcomes? Well, you have 5 upbeat dance songs. So the event space would be 5 upbeat dance songs divided by the total sample space of 12. So 5 over 12, or 41.7% chance. All right, but now let's look at this example. What happens if I have a CD and it has 12 songs and 2 songs are randomly selected? What is the probability that you select your 2 favorite songs? So we're not asking, okay, we're not thinking about how are you going to listen to your 2 favorite songs. You just have 2 favorite songs and you're going to select them. So you can select the first one first, like song A, and then your next favorite B, or you could select B, A. Doesn't really matter how you select them. They're just your 2 favorite songs. Your 2 favorite songs. Order is not important. The total sample space, because we have 12 songs, we have to select or choose 2 of them. Order is not important, so it's 12, choose 2. Okay, so that's 12 factorial divided by 2 factorial times 10 factorial. That will give you your total sample space of 66 outcomes. Well, there's only one way to select your 2 favorite songs. You just select them. Either you select your first favorite first, followed by your second favorite, or you select your second favorite first, followed by your first. Okay, there's only one way to do that. So the probability that you select your 2 favorite songs is 1 out of 66. That involves combination. Now, what happens if I say if a CD has 12 songs and 3 songs are randomly selected, what is the probability that you listen to your 3 favorite songs, so that you listen to your first favorite, followed by your next favorite, followed by your third favorite? So now order matters here, okay? Okay, because you're going to select, so the first song you'll select will be your favorite song. You'll play it and listen to it. The second song you select will be your next favorite song. You'll play it and listen to it. And then a third song you select will be your third favorite song. You'll play it and listen to it. And let's say here your favorite songs were A, B, and C. And you're going to select them. Well, so order is important, because if you listen to A first, followed by B second, followed by C third, well, that will be different than if you listen to B first, followed by A, and then followed by C. The order in which you listen to them will be different. So here, order is important. Order matters. So the total sample space, now we're dealing with a permutation. Okay, order matters, so that would be 12p3. Or 12 factorial divided by 9 factorial, which would be 1320. So 1,320 possible ways in which you can listen to those 3 songs in a given order. There's 1,320 ways you can listen to 3 songs out of the 12 in a certain order. In the event space, there's only one way you listen to your 3 favorite songs. You just listen to them in the order. Your first favorite first, followed by your next favorite, followed by your third favorite. There's only one way you can do that. So the event space is just one. So the probability that if you randomly select 3 songs out of 12 and you listen to them in that order, favorite first, followed by second favorite, followed by third, the probability is 1 out of 1,320. So here, let's take a look at, so we have 2 number cubes, one red and one blue. What is the probability that the difference between the two numbers is 4? Okay, so again, a number cube, you have 6 possible outcomes on the number cube, right? Now, if you roll 2 cubes, so the total sample space, you have the fundamental counting principle. You're going to roll, so you have a red cube and a blue cube. The total number of events for the red cube is 6. The total number of events for the blue cube is 6. The fundamental counting principle says you should have a total of 36 possible outcomes if you roll 2 cubes, one red and one blue. 36 possible outcomes. That's your total sample space. So let's look here. So there's 36 possible outcomes, FCP. What is the probability that the difference between the 2 numbers is 4? So here you have to list where the difference between the 2 numbers is 4. This involves just enumeration. So when I say enumerate, you just have to list. So if we go back here, I said there's many ways in which you can find a sample space of favorable outcomes: enumeration, fundamental counting principle, permutations, or combinations. So here I have to just list the outcomes, okay? Where the difference is 4. Well, 2 and 6 is a difference of 4, 5 and 1, and 6 and 2. And 1 and 5, the difference is 4. Oops. So there's my event space of favorable outcomes is 4. So 4 out of 36, that's 1/9. Each cube has 6 outcomes. The sample space, fundamental counting principle, 6 times 6 is 36. Your favorable outcomes are 4, or the difference is 4. Let's look at the next example. A red number cube and a blue number cube are rolled. If all numbers are equally likely, what is the probability of the event? The sum is 6. Again, your total sample space is still 36. But now you have to numerator list all the ways in which the sum is 6. So you got 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. 5 ways in which you get a sum of 6, so the probability is 5 over 36. A red number cube and a blue number cube are rolled. If all numbers are equally likely, what is the probability of the event? The difference is 6. Okay, 36 possible outcomes, but there's no way in which you will get a difference of 6. The largest number you have is 6. The smallest one you have is 1, so the largest difference can be 5, would be 5. So there's 0% chance. If I said what's the probability that you get, if you roll 2 number cubes, you get a sum greater than 1. Okay, well that's 100% prob. Okay, that's 100%, because you can get a 1, 1, and that's 2, and 2 is greater than 1. So any 2 cubes, when you sum them up, will be greater than 1. So the probability there would be 100%. So again, probability goes from 0% to 100%. Okay. Sometimes when working with probability, it's just easier to work with the complement. The sum of all probabilities in the event space is 1. The complement of an event E is a set of all outcomes in a sample space that are not in E. Okay, so we say the probability of the complement of an event E is the probability of not E, or 1 minus the probability of E happening. Sometimes this is really, really helpful in finding probabilities, okay? It keeps you from having to enumerate or count a lot of things. Let's look again. So we have 2 number cubes, red and blue. If a red cube and blue number cube are rolled, what is the probability that the sum is less than 10? Well, think about that. You can add up 1 and 1, or 1 and 2, or 1 and 3. You have a lot of those possibilities where the sum is less than 10. A lot of them. Why not just say here, it's too many to count. Use a fact. I can say, well, what's the probability that the sum is less than 10 is the same as 1 minus the probability that the sum is greater than or equal to 10. The sum is greater than or equal to 10. So I just list those ways in which the sum is greater than or equal to 10. I have 5, 5, 5, 6, 6, 5, and 6, 6. So the probability that the sum is less than 10 is 1 minus the probability that the sum is greater than or equal to 10. And so that's 1 minus 4 over 36. That's 1 minus 1/9. That's 8/9. You see, it was a lot easier just to take the complement for that problem. What is the probability that the product of 2 numbers and a 2-digit number, 0099, is less than 56? So you're going to have 2 numbers, right? 2 places to fill in. The first spot you can fill in with one of 10 numbers. This next spot you can fill in with one of 10 numbers. Your total sample space then is going to be, you'll have 100 different possibilities. We're looking for what's the probability that the product of 2 numbers and a 2-digit number, 0099, is less than 56. The product, well, that's a lot of numbers. You got 100. Do you want to count all those where the product is less than 56? Okay. So the easiest thing to do is just say, hey, well, let's just use the fact of 1. The probability that the product is less than 56 is 1 minus the probability that the product is greater than or equal to 56. Much easier to do that. So when you think about it, okay, 7 times 7 is 49. So as long as I have numbers where each one of those are 7 or greater, 7, well, so for example, I have 7, 8, well, that gives me 56, and that's certainly 56. 7 times 9, and then I have 8 times 7, and 8 times 9, and then I have 9 times 9. Okay, so I've listed all the possibilities. Okay, so the first digit is 7, the next one is 8. The first digit is 7, the next one is 9. I've exhausted the 7s. Now I'll go to 8. The first digit is 8, the next one is 7. The first digit is 8, the next one is 9. And then the case 9 and 9. Each one of those, you'll get a product that is greater than 56. Okay, I guess I didn't list those 9 and 8 and 9 and 9, did I? 9 and 8, 9 and 7. I did not list those. 9, 9, 9, 8, 9, 7. Okay, 8, 7, 8, 9. And then 9, 9, 9, 8, and 9, 7. 9, 6 is 54. Has to be greater than or equal to 56. So I have 1, 2, 3, 4, 5, 6, 7. I have 7. My favorable outcomes are 7. Okay, so 1 minus 7 over 100 is 93 over 100. So the probability of having a product that's less than 56 is 93% chance. Okay. 93%. Let's look at it. Each student receives a 5-digit locker combination. What's the probability of receiving a combination with all odd digits? Okay. So you got to fill in 5 spots. 1, 2, 3, 4, 5. This is the fundamental counting principle. Okay. So the total sample space then would be 10 ways to choose the first number, 10 ways to choose the second, third, fourth, fifth. There's 100,000 possible outcomes. That's my total sample space. Now, my favorable outcomes will be when all the digits are odd. So again, I still have 5 digits I have to fill in, and then I have 5 odd. So 5, 5, 5, 5, 5, 5. So, okay, 1, 3, 5, 7, 9. Okay, so the first spot will have 5 possibilities, the next spot 5, and so on and so forth. There's 3,125 favorable outcomes, or that's my event space. So the probability is my event space divided by my sample space. So that would be 1 out of 32. A DJ randomly selects 2 of 8 ads to play before her show. 2 of the ads are by a local retailer. What is the probability that she will play both of the retailers' ads before her show? So we have to determine whether the code is a permutation or combination. Order is not important. Okay, the DJ is just going to select 2 ads to play. Didn't say anything about ordering those ads that are selected. Okay, just going to select 2 ads to play. Now, if it said that the first ad selected will be played first and the second ad selected will be played next, then order wouldn't matter there, but just going to select 2 ads to play. Okay, so as an example, they select 2 ads, and then an hour later they'll play one of them, and then an hour later they'll play the other. But the order is not important. Just going to select 2 ads to play. So order is not important. So this involves a combination. The total sample space is 8. Choose 2, or that would be 28. There's only one way to select both of the retailer's ads, right? You select A, B, or B, A. It's all the same. Doesn't matter when the ads are going to play. So there's only one way to do that. It's a combination. If order was important, then A, B. If order was important, then A, B would be different than B, A. And so we wouldn't have one way to select both the retailer's ad and play them. We would have 2 ways, either A, B, or B, A. but this is combination, so the probability is 1 out of 28. Find the number of outcomes in the sample space. So they just did that. So we got 28. Find the number of favorable outcomes. There's only one. There's only one way to select both ads to play. You select both of them. And then the probability would be 1 out of 28. Sometimes drawing a probability tree helps. So let's say here you have a quarter, dime, and a nickel. If you flip all three coins, what is the probability the quarter and the nickel shows head? So you got three coins, right? One, and you're going to flip three of them. There's only two possible outcomes for each coin. You can get a heads or tails, or heads or tails. The fundamental counting principle says there should be a total of 8 possible outcomes when you flip three coins. Okay, and so here actually I'm using a probability tree helps. So assume, I have a quarter, and on the flip I can have either heads or tails for the quarter. Okay, and on the dime I can get either heads or tails. So let's assume I flip heads for a quarter. On the dime I can get heads or tails. And on the nickel I can also get heads or tails. So notice here I have a total of 8 possible outcomes, which is what I should have. And then let's see here, the question says you have a quarter, dime, and a nickel. If you flip all three, what's the probability that the quarter and the nickel shows heads? And so that's the first and the last. Quarter and nickel there. Quarter and nickel there. There you go. It's 2 out of 8. It's 1 out of 4. Okay, the dime shows heads. So the dime is the one in the middle. It has to show heads. 1, 2, 3, 4. 4 out of 8 is 1/2. Sometimes making a probability tree helps to answer the questions. Now let's look at geometric probability. It is a form of theoretical probability that's determined by the ratio of lengths of areas or volumes. So here a figure is created placing a rectangle inside a triangle inside a square is shown. If a point inside the figure is chosen at random, what is the probability that the point is in the shaded region, that purple region there? Okay, so we have to find the ratio of the area of the shaded region to the area of the entire space, or I say sample space. The area of a square is S squared, the area of the triangle is 1/2 the base times the height, and the area of the rectangle is L times W. So the sample space, the total sample space, will be 9 times 9. Okay, that's the area of the big square. 9 times 9. That's my total sample space. The area of the triangle is 1/2 the base times the height. So the base is 9, the height is 9. 1/2 the base times the height. So that would be 40.5. And then the area of that rectangle there is 4 times 3. So what we have to do, we have to subtract the area of that small rectangle from the area of the triangle, and that will give us our event space, the shaded region. 40.5 minus 12 will give you 28.5, and the total sample space then is 81. So the probability that the point is in the shaded region is 28.5 over 81, or 35.2%. Okay, so try those for the lesson quiz.